Thank you all for joining us at SLOLA. And I just wanted to go over a little bit about specifically the goals of SLOLA and how our seed library works. So the goals of SLOLA are to grow acclimated seeds to our specific bioregion and climate so as to cultivate crops and plants that are more resilient, hardy, and fruitful because they're naturalized to our weather here in East LA. And this process takes about 7 seasons. We are also interested in building a community of gardeners and people interested in food security, habitat restoration, and wildlife, as well as a network of knowledge and wisdom so that we can cultivate communal resiliency for us humans, the legacy of the seeds we're growing, and the wildlife that we cohabitate with. SLOLA works via our meetings and then lots of correspondence through email. So our meetings are always open for all to attend and they are free. We'll have guest speakers each month who will share on various topics that we find relevant to the mission. And we also factor in what our members want to learn. To be a member, you must live in LA, and we ask that you live close enough to East LA so that when we go back to in-person meetings, you will be able to join us in person. Membership is a simple process. You pay a one-time $10 donation, and you'll be invited to check out seeds monthly. And we use the term check out because the intention is that you'll actually be returning these seeds that you save to contribute to the evolution of our library. We get many of our seeds from companies like Baker Creek. We would love to grow other selections, other sections of our library, like our native California plants, flowers, and medicinal and herbal plants. Seeds returned to the library must be open pollinated, organic, and non-GMO. If you have questions about this, please email us. And then also we ask that you take the precautions necessary to avoid hybridization of certain plants that like to do that. And we will continue to have seed saving workshops so you can learn more. And I will give it back to you.
Just in hearing about fires over the last few years. So, as everyone knows, wildfire has been in the news since 2017, when California began to break all historic records for fire. Since then, those records have continually been exceeded, with each year worse than the previous. In the simplest sense, we say that there are 2 Californias, the Sierra and northern forests, where fire suppression has caused long intervals between fires, leading to excess growth and unnaturally severe wildfires. And in Southern California, where fire suppression has not affected the amount of area burned, and we have had a vast increase in the frequency of fires. This is the fire paradigm for California. Our forests were adapted to frequent low-intensity surface fires that killed small understory shrubs and trees, and because they were easy to control, we were very effective at excluding fire. High-intensity wind-driven chaparral fires, on the other hand, are very difficult to control, and suppression has not successfully excluded fire from the system. Conversion from a high-frequency, low-intensity surface fire regime leads to large-scale crown fires due to the change in biomass and fuel continuity caused by understory growth. What is frequently not mentioned is that California forests have a long history of timber harvesting that can also lead to forests with the same structural characteristics that can cause high-intensity stand replacing fires. But whatever the cause of overdense forest stands, suppression, logging, or timber plantations, the solution is the same: thinning of trees and reintroduction of regular fire. Unfortunately, when you remove the fuel in chaparral, you remove the ecosystem and all of its functions. So fuel reduction always carries a high environmental cost and should be done with care in these systems. If the forest paradigm for managing wildfire is not right for Southern California, and Chaparral, how do we learn what is? In the Santa Monica Mountains, where I've worked for 20 years, in the late 1990s, we had an excellent fire geographic database, which was uncommon at the time. Because we had good data early and lots of wildfires, the Santa Monica Mountains is often used as a model for studying Chaparral and Southern California wildfires. This is an example of our spatial fire history from 1925 to 1939. It lets us visualize the number of fires, their size and location, as well as the weather and season in which they occurred. When we look at these patterns over time, it defines our fire regime and lets us understand how wildfire can threaten both our human and natural communities. There's now excellent spatial data for the entire state of California. So Robert Taylor, our fire GIS specialist, expanded our fire history study area to include the region of the San Gabriel Mountains so that you can see your own fire history. I think that these series of decadal fire maps are one of the best visualizations of how much area burns each decade and where. So for example, in this period, you can see that about 40% of the Santa Monica Mountains area burned. Here's our Santa Monica Mountains. Relatively little in the San Gabriels, but the massive Matilaha fire burned to the north in 1932. This is the next decade, the 1940s, the 1950s. There was massive fire activity in the Santa Monica Mountains and also an increase in the San Gabriels as well. The 1960s were quiet in the Santa Monica Mountains, but in 1961, we had the Bel Air Fire. This was the first widely recognized and highly publicized wild and urban interface fire, with hundreds of homes lost in Brentwood and new fire policy that developed out of that. The 70s were a decade with an extraordinary number of large fires. In the Santa Monica Mountains, about a third of the recreation area burns per decade. And usually, but not always, there is not much overlap between fires within 10 years. We have not calculated the fire return interval for the larger region shown here. "1993 was the first modern firestorm with multiple fires burning at the same time throughout Southern California with massive home losses. In the 2000s, we had two more major firestorms, 4 years apart in 2003 and 2007. The Station Fire, the largest fire in LA County history, burned in 2009. This is also the decade when we saw the average area burned per decade begin to increase in the state. If you overlay all the fires from 1925 to 2020 in the Santa Monica Mountains, what you get is a map of where and how many fires have burned in the past 95 years. We call this a fire frequency map. In both maps, cool colors are areas with few fires, and hot colors are areas where fire reoccurs at abnormally high fire frequencies. Chaparral and the coastal zone evolved in a fire climate where fires reoccurred at 70 to 150 years. So fires that reoccur repeatedly in less than 20 to 30 years cannot be considered natural. These repeated, frequent large fires are a continuous threat to both native habitat and human communities. Why do we have fires with such regularity, and why are they so large? Our dominant vegetation is shrublands. that have perfect fuel characteristics for easy ignition and rapid spread. Continuous canopies, small diameter twigs and branches, lots of dead stems, and an erect canopy that lets wind move quickly through. Every single year, we have extreme fire weather conditions in the fall with Santa Ana winds, low humidity, and high temperatures. This is at the same time that our vegetation has dried out to critically low live fuel moisture levels from lack of summer rain. Any ignition during Santa Ana weather conditions at this time of the year has the potential to become a large wildfire. In Southern California, it is ignitions that control wildfires, not temperature increases from climate change. Based on our fire history data before 2012, we could describe our wildfires as big, fall, wind-driven fires caused by human ignitions. The size and intensity was natural, but the fire frequency was too high, and there was a long history of major disasters. But in the last decades, fire records have been shattered throughout the state, including our local fires. The 2013 Springs Fire burned in May, our only spring season fire ever. It occurred during a Santa Ana wind event, which normally cannot carry a wildfire during that time of the year because the vegetation has too much moisture from the winter rains. However, the live fuel moisture in May that year was the same as normally seen at the end of the summer due to a severe winter drought. That fire was followed by another 5 years of the most extreme drought in 1,200 years. The 2018 Woolsey Fire broke all fire records for the Santa Monica Mountains, with 2.5 times more area burned than previously and a record number of homes destroyed. The 2020 Bobcat Fire became the second largest fire in LA County history after the 2009 station fire in the previous decade. On the coast in our mountains, we only see Santa Ana-driven wildfires. However, Southern California actually has two kinds of fire regimes, Santa Ana and non-Santa Ana fires. Even though they burn approximately the same amount of area, Santa Ana fires spread more rapidly, are closer to urban areas with greater development, and have a shorter duration. Non-Santa Ana fires are longer duration, often in remote areas with difficult terrain and older fuels. As a result of these differences, Santa Ana wind fires are responsible for about 80% of the total economic fire losses, and non-Santa Ana fires for about 70% of the total fire suppression costs. The Bobcat and the Woolsey Fire illustrate the characteristics of each type of fire. In a lot of ways, the Woolsey Fire was typical of Santa Ana fires in our previous wildfires. It was a fall fire driven by Santa Ana winds and started by an electrical failure. But it was 2.5 times larger and burned almost triple the number of homes as previously due to its extreme rate of spread. Similarly, the Bobcat Fire is typical of a late summer inland wildfire seen here with the progression map on the left that shows the area burned in 15 days of fire spread. This also shows a topographic projection of the fire perimeter on September 12th and NASA imagery over time and the fire's geographic location as of September 14th. Undoubtedly, the spread of the fire was exacerbated by dry vegetation and rugged topography that made it difficult to access. This table summarizes statistics for both fires and illustrates how rate of spread and proximity to urban areas of the Santa Ana-driven Woolsey Fire contributed to much larger structure losses, as well as fatalities and how the longer duration of the bobcat fire in difficult terrain can increase suppression costs. This is a table of the devastation from California fires beginning in 2017. Above the table are the record-breaking local fires, and below the table, the new state fire records. 2017 began a sequence of ever-worsening fire years for area burned, number of homes destroyed, and people killed. The scale and severity of this past 2020 fire year has left people in the state and fire colleagues around the world truly shell-shocked. The tendency today is to attribute any increase in fires to climate change, but it is a much more complex picture. The threefold record increase in annual area burned in the 2020 fires was due to a combination of low rainfall, an extreme heat wave, an extraordinary but infrequently recurring lightning event, historical fire suppression practices, and dieback from a record 5-year drought. There's so many ways that the 2020 fires were unprecedented. This graph shows the enormous amount of energy released compared to the previous 8 years of fires. This can probably be attributed to not only the size of the fires, but also the forest fuel types with many years of accumulated biomass from a long history of fire suppression. The wind-driven fires that caused the extraordinary home losses were not due simply to the condition of the fuels or climate change from an increase in average annual temperature. For example, the 2017 Tubbs fire burned about 5,600 homes in virtually the same footprint as the 1964 Hanley fire, which burned only 50 homes. There were no deaths in the 1964, but 22 in the Tubbs fire. Between the two fires, the population in Santa Rosa quadrupled, and there was extensive low and high density development in a known fire corridor. Part of the wildfire problem is not climate change, but land use that increases the exposure of development to extreme wildfire behavior. Since the year 2000, over 13 million acres have burned from wildfires in California. This is double the acreage burned in the prior 20 years. Our largest fires used to be spread out over decades. Now 9 out of 20 of the largest fires were in the last 5 years. 5 of the 6 largest fires were in 2020. One of our local fires, the Thomas Fire, briefly had the record for largest fire in California in 2017. Why did this fire become so large? It was due to 5 years of preceding drought and the longest Santa Ana wind event on record. It lasted for 9 days. The Bobcat fire that would have been in the state's top 20 largest fires if it had happened before 2007 is almost 50,000 acres smaller than the current number 20 largest state fire, the Day Fire in Ventura County. Besides their size, the recent fires have been unprecedented in their destructiveness and deadliness. Why? The Camp Fire in Paradise, the deadliest and most destructive in state history, had wind-driven topography aligned with the wind, an ignition close to town with a dense wild and urban intermix, no advance warning, and limited ability to evacuate. The Woolsey Fire had an incredibly rapid rate of spread, 70,000 acres in less than 24 hours, and limited firefighting resources in the early stages of response due to the campfire which had started only a few hours earlier. Northern California firefighters that were normally on call in November for Southern California fires were not available. Climate change in our region may give us a few more days when conditions would support wildfire, but each fire is driven by the same factors as always: ignitions, weather, fuel, and topography. Climate models do not fully predict how much area burns, and there are other important contributions to wildfire activity, such as extreme heat and wind events, long-term drought that drives fuels, human ignitions that start fires, and land use. This is partly a hopeful message because while we can't control short-term climate change, we can affect fire outcomes by reducing ignitions and changing land management practices and land use. So many fires. What about recovery afterwards? Once chaparral is gone after fire, people appreciate it much more as the value it gives holding up slopes becomes immediately obvious when debris flows follow fire. Each fire is unique. One difference among fires is their landscape pattern of burning and how patchy the landscape is afterwards. Even though large areas are burned, they burn in complex patterns, and there may often be unburned inclusions. For chaparral recovery, edge and unburned inclusions are not important for recovery, but they are probably important as fire refugia for smaller species of wildlife and as a source for wildlife recolonization. Fire severity is another way in which fires differ. In a typical chaparral wildfire, most of the above-ground biomass is consumed, but we still see burned stemmed and smaller branches remaining afterwards. The Woolsey Fire was very different, however. In many areas, there were no shrub skeletons at all, an indication of high severity, likely due to drought dieback prior to the fire. Photos from the Bobcat fire look similar, with high severity consumption of most of the biomass. When plant ecologists looked at burned chaparral landscape, why don't we think it has been destroyed? Chaparral is used as a classic example of a fire-adapted plant community because of the post-fire autosuccessional pattern of regeneration that occurs. Every plant species that was there before the fire exists in the soil as a seed or underground root or stem that can germinate or resprout after the fire to replace what burned. This fire series, taken at Boney Ridge by Steve Davis, is a great example of the typical chaparral fire sequence that was seen at the 1993 Green Meadow Fire. An individual laurel sumac is indicated by the red arrows. In February 1993, there is a beautiful stand of diverse, mature chaparral. It burns in November and burns most of the above ground biomass, leaving exposed soils. In the first spring after the fire, there is massive germination of the short-lived herbaceous fire follower, bleeding hearts, that dominates. But shrub seeds have germinated and other shrubs have resprouted. Finally, 13 years after the fire, a very similar plant community, including some of the same individual shrubs, has returned. The most dramatic and unique aspect of chaparral fires is the profusion of wildfire fields in the first and second year after fire. These come from seeds stored in the soil seed bank between fires. There are hundreds of annuals, bulbs, and herbaceous perennials that are fire stimulated and become more abundant after fire because of added nutrients, sun, and lack of competition. The magic ingredients that is essential to vegetation recovery is rainfall. This graph shows the very different rainfall pattern after 3 fires. The Springs fire was preceded by drought in 2012 and was followed by another 6 years of drought through 2018. The Woolsey fire was followed by 2 excellent years of rainfall with good vegetation recovery of resprouting shrubs and seedling establishment. This year is looking like another extremely dry year, which will be very bad news for the 114,000 acres burned in the Bobcat fire, especially if it is followed by another multi-year drought. For the Springs fire recovery, the burn scar of the fire is still visible 6 years post-fire. Vegetation is not recovering normally. Usually chaparral recovers to closed canopy by 10 years at the coast. The question is whether recovery is just slowed or if we will see a permanent change in vegetation type. The 2 wonderful rain years in the winters following this fire was a great start on vegetation recovery, with a spectacular spring and summer of native herbs. The park is committed to extensive monitoring after fire, as it is likely the most important mechanism of vegetation community change, especially with climate change. We have 300 plots, and in this plot, you can see what the vegetation was like pre-fire, post-fire, in the first spring after the fire, and finally in the first fall, where you can see that the largest plants are resprouting shrubs, the annual herbs have died back, and that the small shrub seedlings aren't really visible yet. This is some of the plot data that shows the importance of rainfall to recovery. There's almost double the recruitment in 2019 after the Woolsey fire compared to 2014 for the Springs fire. Of course, what matters is what kind of long-term survivorship there will be after the fires. What are the fire effects on wildlife? To a plant biologist, this looks fine because we know that the plants should be coming back. But for a wildlife biologist, it looks pretty bleak. If you were an animal, how would you feel about this change? But even in a fire where vegetation recovery was poor, wildlife cameras at 90 sites recorded wildlife views from August 2013 through March 2015. How does wildlife respond to just the fire itself? To survive, animals can flee and recolonize or survive in refugia. Do animals die? Yes, some more than others. For the survivors, there are new challenges. Is there enough unburned habitat outside the burn area to absorb the survivors? Can they shift habitat preferences? How rapidly does recolonization occur for different species? What species can use burned and recovering habitat? To answer these questions, you need to have the funding and expertise to do long-term post-fire monitoring to track wildlife. And you need pre-fire data. The larger and longer the data set, the better. The Santa Monica Mountains National Recreation Area has an unprecedented amount of pre-fire wildlife monitoring data to study the Woolsey Fire's effects on wildlife. For example, the mountain lion tracking study has been ongoing since 2002. There are pre- and post-fire studies ongoing for mountain lion, bobcats, deer, amphibians and reptiles, small mammals, and birds. Everyone knows one of the major impacts of fire is the flooding and debris flows that occur after storms in the first couple of winters after fire. This has a huge impact on stream habitat for aquatic amphibians like frogs and salamanders, even under normal circumstances. But during a drought, what we saw was sediment being deposited and then not being removed by subsequent storms. In Sycamore Canyon, we saw a years-long loss of pool habitat for amphibian reproduction. In 2013, the park began a project to reintroduce California red-legged frogs to the Santa Monica Mountains. The source and reintroduction sites were all burned in the Woolsey Fire. We know that some of the frogs survived the fire, but except for the source population, their breeding habitat did not, as the pools filled in with sediment. The West Fork of the San Gabriel River is facing the same problem of loss of stream habitat for the endangered Santa Ana sucker and Southern California mountain yellow-legged frog. The U.S. Forest Service and USGS are planning for possible emergency relocation if sediment filling occurs in this habitat. But what about the future? Given what we've seen locally and statewide in the last decade, what are the fire and climate threats in Southern California? I would consider short fire return intervals our #1 threat to shrub ecosystem viability and persistence. Ideally, we would not want fire to recur for 12 and 17 years in the Springs or Woolsey burn areas. But in looking at our fire frequency map, how likely are we to succeed at that? What are the ecological effects of repeat fire? For species like big pod ceanothus that recover only from the seed bank, when fires return too quickly, seedlings from the last fire did not have enough time to grow and replenish the seed bank, and the populations go locally extinct. The loss of long-lived shrubs from type conversion, also after repeated fire. In this location, there were 3 fires in 11 years. The photo on the left shows a typical intact chaparral canopy. The 1996 photo point is what it looked like in the first year after the 3rd fire, and the repeat photo on the right after another 10 years without more fires. Closed canopy mixed chaparral has changed to a degraded chaparral type dominated by exotic annuals and obligate sprouting species, such as laurel sumac. What happens to our unique post-fire herb flora when we lose shrublands to type-converted annual grasslands? The red dots on the map are modern grassland fire monitoring plots superimposed on vegetation types from the 1930s VTM map. The plot photos on the left show what the typical vegetation looks like after the first year in a shrub plot with native herb species. But the grassland plots, type converted from coastal sage scrub, have lost their native herb flora. Type conversion from frequent fire is occurring throughout Southern California. A recent study of the Santa Monica Mountains National Recreation Area showed that about 30% of what was shrublands in the 1930s is now partially or totally type converted to non-native grasslands. Other parts of the transverse ranges have similarly undergone extensive shrub loss. Why is this a problem? We lose wildlife habitat and a whole suite of ecosystem services associated with our native vegetation if it is degraded by type conversion. Our number 2 fire and climate threat is drought. It can increase the seasonal window for fire. It can dry or kill fuels that make fires spread faster, burn more intensely, and grow to larger fire sizes. It can slow native recovery when it occurs after fire and increase the potential for type conversion. While increased temperature does not link to increased area burned in our region, it does increase evaporative demand for soil water and increases water stress in plants. It may contribute to factors that affect fire, like live fuel moisture, dieback, and post-fire recovery. Timing is everything. These photos show resprout mortality after a fire in greenbark ceanothus during the 2007 drought. This is very different from the outcome of the chaparral dieback in big pod ceanothus that occurred during the 2012 to 2018 drought that was then followed by the Woolsey Fire. Big pod is now probably recovering beautifully because there was fire-stimulated seedling germination of the dead plant seed bank and abundant rain in the first 2 years post-fire to get the seedlings established. Extensive dieback also occurred in oak woodlands in the drought from 2012 to 2018. We're trying to determine if drought stress increased oak mortality after the Woolsey Fire and after earlier fires during the drought. This fall, we were incredibly surprised and happy to discover that some trees we thought had died from drought in the unburned areas or after the 2016 old fire were resprouting. They were struggling, but still alive. Lastly, as a fire ecologist, I've spent a lot less time on ecology and more on fire science related to effective fire management for safer communities and conservation. What preventive strategies are available to use? Well, we could just get rid of this flammable stuff. Why don't we? We don't because it has value and provides free ecosystem services that are lost or reduced when it is gone. So it needs to be protected as much as possible. Why do we lose homes and lives? First, because our wind-driven fires have an incredible rate of speed. They're carried rapidly to our homes that are located intermixed with wildland vegetation, while firefighting resources are often overwhelmed during these rapid spread phases of the fire. Second, wildfires create massive ember storms that can land on receptive homes that cause new fire starts and structure losses. We need a new approach for wind-driven wildfires. This is more a people problem than a fuel problem. 100% of these fires are ignited by people, and increased fire activity since 2000 may be accounted for by the addition of 6 million people to the population. The focus should be on prevention of ignitions, planning to give fires similar recognition as other natural hazards, protection of homes with the greatest effort near homes and less as one moves further into the wildlands, and finally, prediction, real-time predictions of wind patterns and fire spread communicated immediately to firefighting agencies and homeowners could save lives. Most importantly for Southern California, communities, government, conservation organizations, and agencies need to work together to reduce home losses by working from the house out to harden homes and create sustainable, defensible space within the first 100 feet of the house. For those who are looking for more information on fire science, park fire management, community wildfire safety, I've provided information links in this resource section of the PowerPoint, and this will be available as a PDF after the talk. So I'll just briefly scan through them. The Parks Fire Management webpage, the new Sustainable Defensible Space website, the Topanga Canyon Fire Safe Council website. And then finally, I want to thank the many colleagues who shared their data and slides for this presentation, and to all of you who came to listen. Thank you.
Thank you so much, Marti. I have a question to get started. I'm interested in that the conversion from Chaparral to Grassland that you were talking about. Mm-hmm. This is the first time I've heard of it, so it's new information for me. And I was wondering, you were talking about the non-native grass species. Are there certain ones that are dominant, or where are they coming from? And could you just talk more about that?
The dominant annual grasses that we see are mostly from the Mediterranean region. So they are adapted to the same Mediterranean climate that we have. They've been in California for probably hundreds of years. They are basically naturalized, and in different areas, you see different species that are dominants. In the Santa Monica Mountains, we have Bromus diandris and Bromus rubens. I'm sorry, I seem to be able to remember either a common name or a scientific name. I can't seem to maintain both of them anymore. So they're species that are they exist throughout the landscape. And when there's a disturbance, for example, a fire, and if they are in proximity and there is a delay or some sort of problem with recruitment and reestablish of native chaparral, they're annuals, so they grow with the first rainfall, they set their seed early, and then it's spread out. So they have the opportunity to take over these open areas after fire. So if our vegetation is inhibited in its recovery, because normally once chaparral or coastal sage recovers, it's a closed canopy system, and that's definitely not a favorable situation for these grasses, which like open situations. So it's basically expansion of pre-existing species. Brassica nigra is also another common one. Avena, wild oats. So bromes and oats are the most common ones.
Thank you. We have a question from Victor. Are we seeing the effects of the fires affecting areas not immediately adjacent to the fire, but miles and miles away?
So are we talking about areas that have been burned or are not burned? So are we talking about areas that are unburned at a distance from the fire, if they're being affected?
Areas not burned, he clarified, yes.
Okay. I would think the primary effect would be whether it's upstream or downstream from the fire. So obviously riparian areas are going to be affected by downstream flooding and possible debris flows. One other, and this is the question, we really just don't have a lot of good wildfire data on what happens with animal populations after fires, especially these fires that are of such a large magnitude that they really are sort of outside the scope of our knowledge and experience. So whether species that escape a fire are putting pressure on habitat in surrounding unburned habitat, that's an unknown question. So those are the main things I can think of. Mainly downstream effects and possible wildlife patterns disruption.
Okay, great, thank you. Anybody else have a question to put in the chat, or you can unmute yourself? Okay, so here's someone, she's apologizing she came in late, but do you see smaller species recovering like insects once plants return?
Oh, we're not even. Insects are really hard. So wildfire is just hard in general to monitor wildfire effects. So you need, as I said, you really need good pre-fire data, and then you need the ability to go out, and you need the ability to go out very shortly after the fire. And because that's really one of our biggest gaps in data, is that people say, oh, I'd really like to go out and monitor that fire, but then they have to look for funding. And so a lot of studies don't start until like a full year after the fire. And what they find is that there's a lot of stuff already out there in the fire, and they don't really know the process by which, the timing by which it occurred. So with insects, you have these very generalized studies that after fire, you sort of get a transition in the types of species you identify, but pretty quickly you return to sort of a pre-baseline condition. But I have to say, there are not multiple studies with really good data. So studies are very few and far between.
I have another question, maybe it's more of a comment, just about the difference between management of the open spaces between the forests, like the wooded areas more up north, and Chaparral. So, because the pine forests are also a fire environment, right? We want fires to burn there as well, but
yes,
we want them to stay low to the ground, correct? And then, or how to—
oh, the fire, yeah, you want the fires to stay low to the ground.
Yes, and not get up into the crowns of the trees. Where
right.
Because you were showing the difference between here in the Chaparral land when the fires were so intense that they took out the larger shrubs, stems and stuff, and then others where they hadn't. Is there a sort of an ideal fire for the Chaparral that's best from its management purposes, or?
Actually, it's less true for coastal sage because super high severity in coastal sage can increase mortality and reduce resprouting, but it's often made up by reseeding. But in Chaparral, a lot of these species are adapted to very high intensity fires. So you in fact find that it's the most intense fires are fires that give you some of the best regeneration. It stimulates more seedlings. And so you actually get better recruitment under high intensity fires. So it's an ecosystem that is adapted. It's a crown fire ecosystem. So that means you naturally have crown fires. I mean, the crowns are lower, but there's still crown fires that are consuming all of the, that canopy and some of the stems and branches. So the intensity of the fire is not a problem for plant recovery. What is a problem is that as these fires become so large that we really don't understand how in these extremely large fires, especially if there are not little islands of habitat refugia that were left unburned, we really don't understand how that is going to affect the recolonization by wildlife. So that is sort of one of the mysteries of our new fire regime that seems to be occurring.
Wow, thank you.
Sure.
Any other final, we're wrapping up, we're getting close to our 11 o'clock hour. So any last minute questions? Someone speak now. Okay, well, thank you so much, Dr. Marti Witter. This was fascinating talk, and we will send out a PDF of the slides. Those maps at the beginning of the different decades were really interesting.
Yeah, so they're wonderful. They're such a great visual aid. I mean, they're amazing.
So we'll be sending that out, a PDF of her slides with our email that we will send out toward the end of next week. So once again, thank you so much.
You're welcome.
And
thanks, Jay. Did you like your picture, Jay?
And those of you who are on, please stay next month in June. Our presenter will be Jessica Handy from Kiss the Ground. She'll be talking about regenerative gardening. So thank you so much. And we will see you all next month in June already. Wow. All right, have a nice weekend.
Thank you. All right, have a good Saturday.
Thank you, Dr.
Enjoy.
Witter.
Thanks a lot.
Well
Bye,
done.
Jay.
Good job. Well done. Thank you.